and it is the Robotics Real-Life Applications of Intelligent Designs in Latvia at Riga Technical University. So it was a great opportunity because I got to learn a lot of skills that are specific to my degree, which is mechanical and aerospace engineering. And I got to meet a lot of like-minded engineering people from all across Australia who were doing this program with me in Europe. We got to learn a lot of skills like doing electronics, making H-bridges to power your DC motors, servo motors. We got to make our own robot. We got to learn how to do 3D printing and CAD modeling and stuff, laser cutting as well. Then we got to do Arduino programming as well. So that's kind of related to your computer systems subject right here. So this program is being offered again this July, and so it's designed to count towards credit for your degree. So you basically just have to call them up and ask them whether how specific it is to your program. But it's basically kind of like an exchange for a month in a new country. And so it's in Europe, and it's like fun. We get to do lots of cultural activities as well towards the side. Like we got to try bobsledding and skiing. We got to go to another European country. So we got to visit Estonia as well. We got to visit Sigurd Soviet bunker, which was pretty cool as well. So the applications for this close on the 2nd of April, and it is a first-come, first-served system. So if you're keen about it, just give them a call or go to the website amfc.com.au and just search up more about the program. The accommodation and everything is included in the program cost. And you can apply for a government OS help loan of $6,000 and around $600. I think it was $6,500 last time, but it's around $66 now. So this does get added to your HECS, but then you don't have to pay for the subject that you're doing this as an exchange for. So that's all. So the applications close on 2nd, and if you're keen, just make sure that you get in before it does close. Yeah. Do you have any questions for me regarding the program at all? No? Okay. That's all cool. Thank you. Thank you for listening, guys. I'll just
So she will send me a link to this. I'll put this link onto my uni page. So if you want to follow up, go ahead. If you want to email her, is that okay?
Yes, email me. That's all good. Thank you. Thank you very much.
All right. Assignment 1, due today, 11:55 p.m. So how's that going? Any questions? Too easy, too hard? Too hard? Yes.
How many assumptions do we have to make?
For that, as far as I can remember, maybe just 1, 2 tops. Not more than that. So all good? So assignment number 2, I will post that tomorrow morning. Although, assignment number 1 is, you can still submit that 3 days late, but there's going to be a cap in your mark, so remember that, right? So today, no cap, tomorrow, 75%, next day 50, next day 25. So for the assignment number 2, I will not go through like I did before for assignment number 1, but if you have questions, let me know. I think assignment number 2 is a bit easier than assignment number 1, but we'll see, right? So you never really know, but I think it's a bit easier. All right, so let's get started. Okay, so first class, we talked, well, so not first class, the first week we talked about understanding the problem. Last week about intuition, right? So just be careful with your intuition. And today we're going to be talking about modeling. So that's going to be like the 3 rules of solving puzzles. And whenever you see a puzzle, these are kind of the steps that you have to take. Have a problem, you try to model it, and then you get a solution. Rule number 1, be sure you understand. Rule number 2, don't rely on your intuition too much. Although your intuition can help you sometimes, but always try to test your intuition. And the way you test your intuition is whatever idea you have about a problem, you have to try to break it, right? So you have to try to make your intuition go bad, essentially try to break it. And today, so the last rule is about modeling. And this is kind of very, very important, okay? So rule number 3, solid calculations, reasoning are more meaningful when you build a model of the problem, which means defining variables, defining constraints, and defining objectives. So that's what we're going to do today for the whole class and then for the next class as well. So let's get started with very simple problem. It's a kind of a trick problem, but let's see. So there's a one-to-one connection between switches A, B, and C, and bulbs X, Y, and Z. So just have this picture in your mind. So 3 switches, 3 light bulbs. And we want to discover which switch works with which bulb. And you're going to have 3 switches. You're going to have possible arrangements. Let's say 1 means on, 0 means off. And the goal is to discover this connection between bulbs X, Y, and Z, switches A, B, and C. All right. So how many possible arrangements are there? So that's the very first question. You have to look at this and just realize what is your state space. How many possible combinations are there in terms of on and off? So if I have just one switch, how many combinations are possible? 2 combinations, right? On and off. So if I have 2 switches, how many combinations are possible? 4, right? So on and off, off and on, off and off. So if I have 3 switches, come on, computer scientists, you have to know this. 8, yeah. So why 8? So it's going to be 2 times 2 times 2. So I have 2 options for each switch, on and off. And then I have to multiply these options together, 2 times 2 times 2. That's going to be 8 options. So this is the possible arrangements you have. Now, here is the puzzle. You have to discover this one-to-one connection, but there's a big constraint. You can turn the switches on and off as much as you want, but you are outside of the room, so you don't know what's going on inside. So the room is completely closed, the doors are closed. You have access to the switches from the outside. You can then turn on and off. And once you enter the room, that's it. You cannot go back. But you have to tell me the combination, which switch goes to which bulb. So how do you do it? You already know this, right? So let's see if someone else tries to think about the solution. This is a famous puzzle. So, do you know this from beforehand?
Just open the door. It doesn't say that you can't open it. It just says you can't enter it.
Well, assume you cannot enter. Otherwise, it's no fun, right? Yes.
I'm assuming you can touch the light bulbs.
You can touch the light bulbs, yeah.
So you just temperature them, right?
Yeah. So how does it work?
You leave one off, turn one on briefly, and then turn the other one on, leave it on.
Cool.
You've got the one that's the hottest is the one you left on, the one that's warm is the one you turn on and off.
Exactly. Yeah. So that's the idea. Turn one switch on, leave it on for a while, turn it off. So you know that the bulb for that switch will be hot, and then you just turn on another one. So the one that is on, that means the light bulb that you just turned on. The one that is hot is the previous one, and the one that is off, that is the cold one that is not on. So that's the idea of how to solve this. All right, so this is just a warm-up. This one is a lot more interesting. And I want us to kind of work together, but I will give you time to see if you can solve parts of the question, okay? This puzzle has been used in the past for assignments, for exams, everything. So right now, it's just for us to solve it. So here is the puzzle. Miss Brown said, I have many brothers and sisters. I myself am the 6th child, and the number of my brothers is at least as large as the number of my sisters. So be careful with inequalities, okay? Inequalities are tricky. And here, because she said as large as, at least as large as, that means an inequality. Her younger brother added, and I have at least twice as many sisters as brothers. How many boys and girls are there in the Brown family? Okay, so remember what we talked about, right? So when you model a problem, you have to identify the variables, the constraints, and the objective. What are the variables here? Yes.
The amount of boys in the symbol and the amount of girls.
Yes, number of boys, number of girls. So let's give name to these variables. Let's say X, number of girls, Y, number of boys. And I also have to identify constraints, right? So how do I identify constraints here? It should be quite straightforward from this text, right? I have many brothers and sisters. It's not a great constraint. Perhaps it tells you that there's at least one brother and at least one sister. I myself am the sixth child. So right now there's a big constraint. There's at least 6 boys and girls, right? And the number of brothers is at least as large as the number of my brothers is at least as large as the number of my sisters. Okay, so how do you deal with this constraint? So let's try to do this, right? So the number of my brothers is at least as large as the number of my sisters. I will give this one constraint, and then I will let you try to solve the rest, okay? Okay. So let's say X, number of girls, Y, number of boys. Okay, so then Miss Brown said, I have at least as many, the number of my brothers is at least as large as the number of my sisters. So how do I put this constraint? So let's say, because she said that, right? So Miss Brown said that. And she's talking about number of brothers and sisters. She is a girl, which means that, what does it mean? How many, X minus 1, yeah. And the number of brothers will be actually the number of boys. So here you're going to have Y. So then what is the inequality? So let me go back. So number of my brothers is at least as large as the number of my sisters. So brothers at least as large as sisters. So here is sisters, here is brothers. So the inequality goes which way? Who? Yes. Less than or equal, right? All right, so this is the very first inequality. What I want you to do is to figure out the other inequalities, the other constraints, and then tell me number of boys and girls in the Brown family. So let me go back to the question, and I will let you work for a couple of minutes, okay? Yes.
They have there are 3 boys and 4 girls.
Yep.
Because if y minus 1 is less than or equal to x, and x minus 1 is less than or equal to y times 2, you get that.
You're missing one constraint. I mean, the answer is correct.
Oh yeah, you got a minimum of 7 children.
Yeah. Cool. I mean, you need these 3 constraints to solve it.
Yeah.
But yeah, that's correct. Cool. Did you try different values, or did you actually put the inequalities in the right place?
I had just got the inequalities and was just like, what variables make this? And so I'm just like, that like is in, you can work that out from like the simplest answer there.
Okay, cool. Yes.
3 boys and 4 girls.
How did you get that?
Because I was just putting numbers in. I know there has to be at least 7 because she's the 6th and she has a younger brother. And when you put them in, you have to look for a number that, when subtracted by 1, is equal to twice the other.
Yes.
And so 7, if you split it, you get 3 and 4, and 3 minus 1.
It's not equal to 7, right? It's not equal to 7. There's nothing there that says it's equal to 7. It's at least 7. I mean, because the problem is set up in such a way that the inequality actually meant an equality, but I mean, it's supposed to be an inequality.
And another thing though, are we assuming that they're not including the parents in the addition?
Of course. Yeah.
They're part of the family.
Yeah, that's a good point. That's a good point.
And
Yeah.
if you model it, you actually should write that assumption down.
That's a good point. Yeah. Yeah. Yes.
But I think it is x equals y equals 4. Is that right?
Yeah.
No?
Oh, I will go over that. All right. So let's try to solve this together. Some of you already solved it, but there's a really, really good assumption that you have to make. Can you say what the assumption is?
We've got to assume that for the final answer, they're not going to include the mother and the father, which would increase the number of boys and girls.
Exactly. Yeah, so when you say how many boys and girls, we're actually talking about the kids, not the parents, which is, you have to make this assumption, otherwise the question will not work. All right, so Miss Brown said she's the 6th child. Her younger brother added. So when there's a younger brother, 6th child, what does it mean?
At least 6. At least 7.
At least 7. So there's at least 7 kids, right? And then I have at least twice as many sisters as brothers. So how do you write this inequality?
X large or equal than 2y minus 2.
X greater than or equal to
2y minus 2.
2y minus 2. Yeah, so 2. Yeah, exactly. Yeah, so these are basically the 3 inequalities that you have here. You know, I tried to put these different colors so we can see all the constraints that you can use. So, you know, the 6th child and 6th child is an important constraint that tells you that there's at least 6 child at this point in the question. Number of brothers and so on, that we already solved. Her younger brother, that means at least 7 children. And I have at least twice as many sisters, so that's the 3rd inequality. So that means you have 3 inequalities, 2 variables, and that's your problem, right? So that's the puzzle that you need to solve. So here are the 2 variables. Here's the inequality number 1 that we already solved. Number of brothers at least as large as the number of sisters. 6th child, younger brother, 7 kids at least. Which means that you can put here x in common, right? So x is going to be less than or equal y plus 1. And x will be greater than or equal 7 plus y. Sorry, 7 minus y. So if you put x in common between these 2 inequalities, you get that 7 minus y less than or equal x less than or equal y plus 1. So you can just throw x out. So that's usually how you deal with inequalities. So you just take this guy outside of the equation, and this inequality here is okay from that. So you can imply this inequality from that inequality, which means from this inequality that y will be greater than or equal 3. So then you get the third constraint, which is I have at least twice as many sisters as brothers, which means that the number of girls is going to be greater than or equal 2 times the number of brothers, which is exactly this constraint, which means that I can take this constraint here, x greater than or equal to y minus 1, and do the same thing here. Replace this 7 minus y by this 2y minus 1. And then I have this inequality where I just tossed x out. And then I have y plus 1 greater than or equal to y minus 1, which means this inequality, which means that y is going to be less than or equal 3. So if you remember here, y is going to be greater than or equal 3. And from this inequality, y is less than or equal 3. So, then y can only be 3. It's going to be greater than or equal 3, less than or equal 3, so it has to be 3. And by replacing y equals 3, into one of the inequalities that you have before, you're going to have the same results for x in terms of, in these two inequalities, x is going to be greater than or equal 4, less than or equal 4, which means x is going to be equal to 4. All right? Be very careful with inequalities, okay? So a lot of the puzzles that I give, I will show you inequalities instead of equalities because they are a bit trickier to work. The next question will be about this, but it's going to be a lot more mathematical in terms of how to solve it. Okay, any questions on this? So let's move on to the next question, but before, always try to remember this rule. I think this is one of the most important rules. Always try to identify your variables, your constraints, and the objectives. So the question before, we didn't have any objective, right? So you're just trying to find a possible solution. Sometimes you want to maximize an objective or minimize an objective. So let's say you want to maximize a profit, you want to minimize the cost, and then you're going to have a lot of constraints. And then that's going to be a proper optimization problem. And that's what we're going to do next. So what we're going to do next is an actual optimization problem, and it's called a linear optimization problem. And a lot of companies, they don't use this type of problems anymore, but a lot of companies use that sort of problems in the past to optimize their productions and so on and so forth. So let's try to solve this together, okay? So this is quite interesting, and if you're planning to do things like machine learning, computer vision, this is going to be very important. And if you're doing engineering, also very, very important. Optimization problems is at the heart of many computer science problems. All right, so let's try to work on this. So there's a manufacturing enterprise that produces two types of items, chairs and tables. Profit per chair is $20. Profit per table is $30. To build a chair, you need 1 unit of wood and 3 man-hours of labor. And to build a table, you need 6 units of wood and 1 man-hour of labor. The production process has some restrictions. All the machines can only process 288 units of wood per day, and there are only 99 man-hours of available labor each day. So the question is, how many chairs and tables should the company build to maximize its profit? Okay. So I think I will try to keep this here while I switch the document here so we can see both. All right, so that's the text of the question. And here is how we're going to solve it. Okay, so what are the variables?
Number of chairs and tables.
All right, so let's call x number of chairs y number of tables. And profit per chair is $20, profit per table is $30. The question is, how many chairs and tables should the company build to maximize its profit? Now, I have to talk about this thing called an objective function. So an objective function is something that you're trying to maximize or minimize, right? In this case, you try to maximize the profit. How do I compute profit? Using these variables and what's said in the question. Yeah, okay, so let's say, you have this operator called maximize. But maximize what? Yeah, the profit. How do I compute the profit?
It will be the number of $20 shares plus the number of $30 shares.
All right, so 20x, right? So chairs are 20. Yeah. And table are 30. So number of chairs times 20 plus number of tables times 30. All right, so this is your objective function, okay? This is a bit. So this is your objective function. That's the function you're trying to maximize. Now, you also have to tell what are the constraints. So usually when you write an optimization function like this, you have to say the constraints by writing subjected to. So then you're going to write the constraints. So what are the constraints? So let's try the first one, which is, to build a chair, a single unit of wood is required and 3 man-hours of labor. To build a table, 6 units of wood are required and 1 man-hour of labor. And you have 288 units of wood, 99 man-hours available. So how do I represent the constraint for, number of woods? So I have a limit in the number, units of wood, which is 288. And that has to be less than or equal that. But how is that constraint going? So how do I write this constraint? So x plus 6y, right? So you have a single unit of wood to build a chair and 6 units of wood to build a table. So a chair x plus 6y has to be less than or equal to 288. And so the second constraint is about man-hours. So we have 99 man-hours, going to be less than or equal. And what is the second constraint? 3x plus y. Are there other constraints? X and y bigger than 0? Bigger than or equal 0. Any other constraints? X must be less than? 33. Why 33? Oh, but that should be already included in there. So you don't need to repeat. It's not gonna help you. It's okay, but it's not gonna help you. Is there any other constraint? There's an important constraint you're missing here. Can you build half a table? So what is the constraint? Yeah, so x and y. Oh, it's going to be natural numbers. All right, so this is the puzzle that you need to solve. Any idea on how to solve it? Just a sec. Okay. Well, yeah, that's what we're trying to reproduce here. Yeah, do you know how to solve or?
No, but
Yeah.
just an idea. You could try to maximize the resources you have. So work out what number of each would maximize.
You mean try and error?
Well, you could start by
All right, so let's try to. It's going to be hard to put these two things together, but let's try to do this. So let's say here's x and y. So when you have So when you have 0 of x and y, obviously your profit is going to be 0. So when you have 1x and 0y, which is at this point, 1x and 0y, you're going to have 20 of profit. So what do you need to think when you solve a problem like this is to imagine that you have a third dimension here, which is your profit. So this is the 20x plus 30y. So that's your profit, right? So it's kind of sticking out from the paper. And, when you get to this point, you're actually having some sort of line, right? So this is going to be 20. When you have 2 and 0, that's going to be 40 and 60 and so on. And when you go in y, into the y direction, it's staying at 0. So when you have 1y, 0x, that's going to be 30 and then 60 and then 90 and so on. So can you see that what you have here, I mean, if I can draw something like this. It's like this plane kind of, getting off this paper, like moving in this direction. It's going to be just a plane, right? In this three-dimensional space, just going up. So this is your kind of your profit, right? So this is your profit graph, so this plane just going out of this paper. Now, you need to include these two constraints in this graph here. So these constraints, what they will do is they will kind of put limits to this graph. It's going to be a limit that says, well, you cannot go beyond this point, or you cannot go beyond that point. And then as you have, these constraints around, it's like, blocking where this plane can grow. And basically what you need to do is to somehow take all the points, let's say, all the points that are inside this constrained space and tell me which one has the highest profit. Okay? So can you try to do that? I will give you a couple of minutes to see if you can find a solution. But this is the idea, right? So you have this plane going out, you have these constraints kind of blocking the way of where the plane can go, and now you're going to have this set of points inside this constrained space where you can compute the profit. And the goal then is just to find the point that maximizes the profit that are within these constraints. Okay, so I will give you some time to try to work on this, and I will give you the answer in a second. Not in a second, a few minutes. So one thing that you need to be careful is not to confuse inequalities and equalities, okay? So you'll be very tempted to take these inequalities as equalities to solve this problem. No, that's good. I like this. So did you understand what I said there? Or, yeah? Okay. You got it.
I'm still working on it. I'm too tired to like actually.
All right. Did you get it? Yes.
I found the answer to be 18.
Did you run a linear program?
Yeah,
Yeah.
yeah, it iterates.
Oh, okay. So that's cool.
Yeah, that's the code. It iterates through, like, it's successive in how far it iterates, but every iteration checks whether or not the amount of chairs is less than the amount of chairs and tables is using less than the amount of man hours and is using less than the amount of wood, and it also checks that the new profit is greater than the old profit, and if it is, it adapts it corrects
Do,
the.
do you mind explaining this?
I can.
Yeah, can you? So what is your name?
William.
William.
Yeah.
Okay, so William, he has a solution that is.
Oh, that's not
Yeah, no, it's gonna work. Yeah.
Yeah, no, I'm just gonna make it bigger.
You can just. So he has a solution that kind of does what I said before. You know, you just go through all possible solutions, check the constraints, and see if that's good. Can you?
So what this does here is it iterates through A and B to 1,000 places. It doesn't need to go that far, but I just did that as the starting point, where A is the number of chairs that it will make, and B is the number of tables it will make. And for every iteration, it calculates Z being the new profit, and it checks whether or not the used amount of man hours is less than 99, and the used amount of wood is less than 288. It then also checks if the new profit is greater than the current highest profit, and then if it is, it adapts the profit variable there, and then at the end it just prints the profit variable and how many man hours and wood it uses.
All right. So that's perfect. This is a brute force.
That.
Yeah.
Well, that's easy to
1845.
see, but, you know.
So that's the correct solution. So you know, this is like a brute force way to solve this problem. Does anyone here know like a more efficient way? Which is called, I don't know if you ever studied this, but it's called the simplex programming. Anyone? So usually there's always someone who knows. But I mean, the idea is exactly the same, except that you don't need to check every point. All you need to check are the intersections between constraints, which means in this case 4 points. 0, 0, the constraint between x 0 and whatever the constraint, the intersection between the two constraints, and the constraint y equals 0, and the other constraint that crosses y equals 0. So there's only 4 points to check, and that solves the problem in the same way.
Yeah, instead of checking at literally a million points.
Exactly. All right, thank you very much. So let's give him a hand. All right, so the solution is this, 18 and 45. And here is the point that I was trying to make. So you have the objective function. So this is the isoprofit lines that you have from the objective function. This doesn't work, sorry. So the isoprofit lines of the objective function. And here are the constraints. So what you see in red, that means, you know, an area that you cannot go. So this is constraint 1. And for constraint 2, the green area is the good area. Red, again, is prohibited from the constraints. And the problem that you have is this, you know, remember that's the hyperplane going up. And now you have these 2 constraints kind of blocking this isoprofit line to go any further. And you also have the constraints of x greater than 0, y greater than 0. So now you have this polygon here, which kind of constrain the solution space, right? So the solution space is inside here. Now you can try to find the maximum profit by just looking at all the points that lie inside this little polygon, or you can just go through the vertices. If you go through the vertices, you're guaranteed to find the max. So that's how we solve this type of problems, even today. So this is a zooming in like this small region. And that's the point that you have here, which is the, you know, the point that maximizes the profit. I usually give a question like this for the assignment or the exam. So make sure you understand what we describe here, because it's very likely you're going to have a question like this, either on the assignment or the exam. So is there any questions about this? All right, so when you come up with a model, you always have to ask this question, is it good? And, you know, profits may change over time, or as you produce more chairs and tables, the profit may decline. The skill of the worker is not well represented here because it's just an average value. You always have to ask this question. And, of course, there's many, many possible models for a given problem. And that's kind of the root of any machine learning problem. You know, if you hear about deep learning, machine learning, it's all about this all the time. The optimization problems they are a bit more difficult, but the ideas is the same. You have the constraints, you have the variables, you want to optimize something. And of course, a model has to be precise, meaningful, not so complex, and it has to be general, so it's that all the irrelevant details are out, and it's specific enough such that it produces a solution that is useful for something, right? So it's meaningful. And here are the issues to consider when you come up with a model. How precise it is in terms of the real-world environment, in terms of the accuracy, for example, that you want to measure something. How difficult is it to find a solution in the model? If it's too difficult, it takes days to run, so you cannot run it very often. So if it finds a solution very quickly, then you can run often, and then you can apply that in real-time systems, for example. What is the frequency that you use the model? If you use it very frequently, it has to be efficient. If not, then you have to find a better way. And how much time is needed to find a solution, and so on. So all these things you need to take into account when you build a model. Again, this part here is useful if you're planning to do like stuff in machine learning, in optimization, and things like this. Otherwise, it's just good to know about how to model something. Okay, so challenge for today, you have about 5 minutes, 6 minutes to solve. And it's, it's about exactly the stuff that we've been discussing. Okay. A farmer bought a certain quantity of cows, each costing $143, and a number of goats costing $89 each. In total, the cows cost the farmer $43 more than the goats. The question is, what is the smallest number of cows and goats that the farmer must have bought? Again, this is proper optimization problem. You want to minimize something, and you have the constraints. So identify the variables, identify the objective function, and the constraints. And you can use brute force here if you want to find a solution. use the same program. Okay. So what is the result?
42 cows and 67 goats.
Yep. So you can explain.
It's the same program.
But so William got the result. I will give like 2 or 3 more minutes to see if someone comes up with a different way of solving this. So he solved by brute force. I just want to see if you paid attention to what I said and solved in a different way. But he's going to get 1%. If someone will get a different solution from brute force, you also get 1%. So let me just take your ID so that you're here.
Do I wait for them to try and solve it, or?
Yeah, just wait like 2 minutes, 1 minute.
Yeah, I've been using Python for the last 4 years and programming for the better part of the last 7. So
Oh, cool. How come?
my dad actually studied here exactly 30 years ago doing computer science. So
10 years ago. So much, almost as much as me. So what did he learn?
computer science.
Yeah, but which language?
I don't recall. Like he currently uses C.
It's not basic.
No, I have done a bit of basic. No, he currently uses C#, but I don't know what language he learned back then because he hasn't said.
Probably a combination of Pascal and
Pascal
Cobol.
sounds familiar. Cobol also sounds familiar.
These are the 2 main languages of the past. I mean, if you go way back, then it's basic, but basic it's not a great language.
Yeah.
So maybe
Things blinking.
yeah. All right, guys. So let's hear William, and you pretty much know how the solution goes, but
Yeah.
can you explain?
You guys know exactly how the solution goes if you were listening before. No, you don't have to do that if you don't want.
That's all right.
The code is basically the same iteration function as before, but you're iterating through and you're determining if A times 143 minus B times 89 is equal to 43. And if so, just exit out of the whole lot and print and return the values of A and B at the point where that statement returns true.
Yeah. I mean, this puzzle is a little bit different from before because it has one constraint.
Yeah.
So 1 constraint, 2 variables, what does it mean? So it means an under constraint problem. And under constraint problem, there's no way you can find a solution like we did before. So this puzzle in particular, you will have to do some sort of brute force. So I guess there's really no other way. I just want to see if someone else had a solution. Okay, so let's thank William, and that's it for today. Thank you very much.
Thank you. Thank you very much.